So thank you very much, Luca, and thank you very much, Namex, for your hospitality. And I'm really excited to be here. And we're going to talk today about open networking and the 400 gigabit, 200 gigabit era. In other terminology, PAM4. So we'll speak about it. With me again, Riccardo Bernasconi, our champion and Italian manager. And let's start. My name is Daniel Kobe, and I'm Senior Director of Networking in EMEA, basically responsible for the networking product line in Europe, Middle East, and Africa. And I'm in NVIDIA networking as, other name Mellanox for 13 years, started as an engineer, and then moved to other positions. Let's talk a bit about the company. So Mellanox is a company founded in 1999 by Eyal Waldman. We're a leader in developing intelligent data centers. We started as an ASIC company. So we did ASICs, design and manufacture ASICs for the InfiniBand technology. We're not going to talk about InfiniBand technology. In this session, it's going to be everything about Ethernet. Then we moved on to do ASICs for Ethernet, NIC card, switches. So we're doing both Ethernet and InfiniBand. Supplier of end-to-end interconnect. It means that we are doing PCI to PCI, all the network components. That means the NIC card, cable switch, cable NIC card, processors, and other networking units. We are actually spread around the world in 5 of top 6 global banks, for example, 9 of top 10 hyperscalers companies. So our growth is very big. And 2 major changes that happened actually really recently in the last month. So the first one is the closure of the acquisition of NVIDIA, acquiring basically Mellanox. And now we are Mellanox as part of what is called NVIDIA Networking Division. And the other announcement that just happened this week, the closure, is actually the acquisition of Cumulus Networks that we'll speak about later on, which is basically now as one company together with Mellanox inside NVIDIA. So this is who are we, and let's go directly to PAM4 and open networking. So I will start with the switch portfolio of us. I'm showing it. I'm not going to go into details about each of the products, but I just want to give you an idea about the different generations of ASIC that we have and basically what PAM4 means. So as you see on the left, right, you see the Spectrum series, which is basically is called NRZ. NRZ is basically the known standard for 25/100 gigabit. So you can look, for example, for a standard aggregation switch, 32 ports of 100. This is 32 ports of 100 gigabit NRZ. If you look at the 2410, for example, is a traditional top of rack with 48 SFP28 plus 8 QSFP28. So those are 8428 gigabit NRZ. Okay, so this is the terminology, basically the terminology that we actually all use already today. It's just called NRZ standard. Okay, we have other switches there, the half 19-inch switches, which are really unique, but the 16 ports of 100, for example, but again, the same technology. Then we are moving to the middle one, which is a Spectrum 2 ASIC. Now the Spectrum 2 ASIC is a PAM4 ASIC. What does it mean, PAM4? It's just a different way of technology of signaling. Here you can see that we're introducing a switch which is called SN3700, which is 32 ports of 200 gigabit. Basically 200 gigabit is the first step in PAM4. This 200 gigabit, and I will explain in a minute exactly the details, it's actually composed of 4 lanes of 50 gigabit. Going back to the NRZ on Spectrum switch, the 100 gigabit is composed of 4 lanes of 25. So 4 double 25 100 in NRZ, 4 double 50 in PAM4 equals 200 gigabit. Okay. This ASIC, by the way, as you can see on the bottom one, we have a module which is called 3510. It actually is capable to do also 400 gigabit. Now 400 gigabit is also PAM4 and is composed of 8 lanes of 50 gigabit. Okay, so 200 is 4 lanes of 50 and 400 is 8 lanes of 50 gigabit. And on Spectrum 3 on the right side, again, a PAM4 ASIC, which is basically doing 32 ports of 400. This is a full-blown 400 gigabit switch. and other products. But another interesting thing that you see here is that there are products here which are PAM4 based, Spectrum 2, Spectrum 3, but you also see 100 gigabit switch. For example, the Spectrum 2, the first one is 3700C, 32 ports of 100 gigabit NRZ, the same standard that we're all familiar. Why is that? It's because PAM4 is also backward compatible. But there are some details here, and I'm going to try to explain how it works. If you can please unmute yourself. Okay, Maurizio, if you can unmute yourself, thank you. Okay, let's go and see how it goes. Okay, so this is regarding the switch products. A bit more about the details of PAM4 NRZ. So this is really kind of a deep dive details, but just to clarify. So as I said, as you can see here, PAM4 as 40 gigabit 50 gigabit PAM4 actually uses 2 bits per clock. So basically what it's doing in a nutshell is moving more data based on clock. And this is why we're seeing more bandwidth basically on PAM4. While NRZ is based on a lane of 25 gigabit, as I mentioned before. So those are the details. And obviously that influences everything. It's not only the switch, so cables, also optics, also copper cables, also obviously NIC cards. Let's look at the trend when it comes to cost versus speeds. So as you see here, where we are currently, we're in a stage where it's not really clear about what is more cost effective. Because if you look at the 2019, for example, I think we could stretch it a bit into 2020, 100 gigabit, and I'm talking about the entire ecosystem, which is cards, switches, cables, and so on, are still less expensive than the PAM4 200 and 400 gigabit. But as we move forward towards 2021 and 2022, you see that there's going to be some difference there. And we're going to see that the cost is actually reduced on that speed. This is a nature evolution of networking technology, right? But let's bear that in mind because that means a lot, okay? So what are the designs or architectures that can be relevant for 200 and 400 gigabit? So the movement from 100 to 400, from 100 gigabit NRZ to 200, 400 gigabit PAM4 is, I think, can be divided to basically two kind of reference designs or architectures. The first one is if you want to actually reduce the number of components on the aggregation level, basically on the spine level, and also the cabling between them, right? This is pretty simple to explain because let's say, for example, that you have a subscription ratio that requires, I don't know, 8 uplinks of 100 from each leaf to each spine, right? So you need 8 cables basically, and you need 8 switches. Now, if we move to 200 gigabit, we can achieve the same ratio, but actually using only 4 switches on the aggregation, and obviously only 4 links. And if you're moving to 400, you can actually do the same thing with 2 switches with 2 links. So by that, you're actually saving cost, right? Because you're having less switches and less cables. But remember the last slide when I said that the cost of the cables and switches are still higher. So we have here kind of a balance between the cost per device versus the reduction of the device numbers. And this is kind of the balance that I will try to explain in the next slide where exactly it actually makes sense. So this is number one, reducing the number of basically components between leaf and spine. And the number two reference can be end-to-end. What does it mean? It means that you have applications or workloads that actually requires a lot of bandwidth. And you actually see the PAM4, the 50 gigabit or the 100 or the 200, today it's up to 200, still not 400, up to 200, starting actually from the server. Or maybe from the DGX, the AI. Okay, so I'm kind of leading into the actual use case. So the actual use case that we see today for 200 and 400 can be actually 3 use cases. The first one is the hyperscalers, the Facebooks and the Microsoft. It doesn't have to be so big, even less than that, maybe tier 2, maybe even tier 3 sometimes. When you have a very, very big networks, then obviously when you're doing the calculation and you can reduce the number of components, you will see some cost benefit. So moving to 200 and 400 means less switches, less cables in a large scale. That makes sense. You will find it also in HPC environments, which are big enough. But also there is another use case which I mentioned, which is the end-to-end use case. So for example, lately NVIDIA, which we are now part of, announced the DGX A100, which comes with a NIC card, which is capable to do 200 gigabit. And by that, basically, you can use directly and connect it to a 200 gigabit switch. So this is a very simple use case. We actually need to use PAM4 200 gigabit. Okay, so this is kind of the two main use cases, like an end-to-end use case based on AI typically, that will come obviously with storage, but still on the AI side, and also HPC and hyperscale. Now, we cannot talk about PAM4 200 and 400 without talking about basically the other components here that are really relevant, right? So I will not go over all the details of the NIC cards that we are providing to the market. And this is, if you remember my first slide, this is one of our advantages in end-to-end company. We can actually provide the full pipeline. So we're actually the only company today that actually provides a 200 gigabit NIC card. What does it mean? It means that we provide the NIC card named Connectix 6, for example, with dual ports of 200 gigabit. And this is a PCI Gen 4 32 lanes. We have basically our high runner. It's called Connectix 6 DX. So this is basically an ASIC that is an ASIC and a NIC that is doing one port of 200 gigabit PAM4 in 16 lanes of PCI Gen 4, or two ports of 100. Now, as I said, PAM4 and NRZ, this is a bit complicated sometimes, so please try to bear with me. Those are two ports of 100, but this is not 100 NRZ. So if you actually take a look, deep dive into this 100 gigabit port, you will find that it's not composed of 4 lanes of 25. It's actually composed of 2 lanes of 50. And this is the place that there is no backward compatibility. That means that this 100 PAM4 does not equal 100 NRZ. You cannot connect it, let's say, to your legacy switch of 100. If you want to connect a 100 gigabit PAM4, basically PAM4 based or PAM4 switch based or ASIC based to your legacy, then you need to use the 200 gigabit port. It's composed of 4 lanes of 50, reduce each lane to 25, and then basically you are coming back to the backward compatibility of 100. I know it's a bit complex, but we are here as always to explain if needed, me and Ricardo, so please reach out. We can explain definitely a bit more on offline, but this is the technology, and we have also another product which is called Connectix 6LX, and this is basically based on the technology of PAM4, but as you can see, we're actually providing the traditional NRZ connectivity with 25 and 50 gigabits. And as I said, the ecosystem cannot be completed without cables and modules. So obviously you need a series to do 200 and 400, a series of cables and modules that are relevant for 200 gigabit and 400 gigabit cables and transceivers. It can be copper and can be AOC, which is active optic cables, and it can be optical transceivers. Now I'm going to kind of shift from hardware a bit to software and talk about open networking, and then I will try also to close it in relation to PAM4. What does it mean open networking? So actually, when people are talking about open networking, different ideas can come up to our mind. We can think about disaggregation, white box. We hear a lot the term bright box, standard RFCs. Open source is something that comes up a lot when thinking about open, right? So open networking also. Linux is kind of an open operating system. No locking in a way. So everything is true. Basically, this is the answer. There are different domains. You can find different terms in telcos, in data centers, but I would like to focus on the data center. This is where we are kind of playing. And in this focus, when talking about open networking, we're talking about open Ethernet. What does it mean open Ethernet? Open Ethernet or open networking in our mind means that the switch, in this case, is not locking in any way. That means that you have all the features there. We're not locking cables, for example. You can use other cables if you like. I think in most of our installation in the world, actually, you will find our NIC cards without the switches, our switches without the NIC cards. So nothing is locked. Everything is not locked in the term that actually our switches are called bright box, sometimes called white box. We are calling it bright box. Different terminology depends on the vendor, but and the value that you are providing. But the idea is that the switch is called ONI switch. ONI is like a pixie boot for a switch. We actually don't even lock the software on top of that. This is what ONI is doing, is able to actually collect a different type of operating system and installing them on our switches. You can see here a scale of operating systems. It starts from Mellanox Onyx, our own operating system. This will be kind of the standard operating system. If I need to compare it to some competition, I would say that this is like the Nexus or EOS or Junos. We have the Cumulus operating system, which is the commercial Linux-based operating system. I will talk about it a bit later on. And we have the open source option, the Sonic, that started as Microsoft Sonic, but today it's a fully open source operating system. And the Dent, which I will not talk a lot about, but it's based basically on a driver which is called SwitchDev, which is a driver for a switch, which basically allows you to take any operating system, Linux-based operating system that you like, install it on the switch with a driver, and run it as a plain Linux. Okay, but I will not focus on that. So we have here kind of a scale of operating systems. And let's look, a bit about how it looks on the, let's say, block diagram. So the interesting thing is that whatever you look, if it's an open source or commercial NOS or traditional NOS, it actually looks the same. In all kind of operating system, typically what you will see is that you have the services, the application. It can be a protocol stack, a CLI, maybe a GUI, and it runs some kind of a software, which is the forwarding agent, just component. For example, a software component that describe what port is, what a VLAN is, what a lag is. And everything runs on top of Linux. Yes, there is Linux on everything, including next to Cisco. There is Linux inside, also Onyx, Mellanox. But as more as you see red, it means that it's more closed. And as more as you see green, it means that it's more open. So if you see Onyx, for example, our own operating system, it's a traditional NOS, but everything is actually red because it's a closed operating system. It's our own, we have our protocol stack inside. Our software is obviously proprietary, but you know what? We can open some Linux, as other vendors are doing, right? We can show you some Linux. You can run the Docker container because it's Linux inside. There is Cumulus, you see more green because the protocol stack is FRR, free range routing, a branch for basically Quagga, or you can use a different one. For example, I have a customer that is using BERT. Everything is open source. Kernel is open source, but you see that there are some red components. For example, Cumulus is a disaggregation company, can actually support different hardware models. For example, Dell, EdgeCore, Mellanox, and so on. That means that there will be a component which is dedicated to per hardware, and this is the red part. And when you go obviously to the full open source, Sonic and maybe Dent, you see that everything is green or 99% green. That means that everything is really open. It's actually in GitHub, including source code and everything. But what I said is that actually Onyx, in Onyx, for example, I can basically provide some Linux to the end user. And there is a CLI, obviously, right? In Cumulus, actually, there is another service which CLU, which is a CLI. It links. So Cumulus is Linux CLI difference. Actually, there is a huge difference. And I can tell you that as a software developer. And the idea is that basically, yeah, both of them can provide maybe a CLI, both of them can provide Linux, but in the way that it was actually designed in the first place, Onyx or any closed operating system, is that it's closed. And this is a very big difference because every time that we need to open and show and expose more Linux to protect, versus Cumulus that everything from the basis was open. And it gives you much more options, much more capabilities when it comes to automation, when it comes to DevOps, when it comes to actually Linux benefits. this is the Cumulus basically idea of disaggregation, as I mentioned, not a closed blob, but basically choose the best operating system, choose the best hardware, choose the application on top of that. And this is kind of what has been done in the server world for many, many years, right? But now, and at least I guess for also quite a long time today, this is also what's happening in the networking world. So Cumulus has many, many benefits. I will not go into Cumulus benefits. I mentioned automation, obviously, and DevOps, and the fact that it's running with a very, very strong protocol stack, which is called FRR, as I mentioned, which is open source also today, and it's actually being used also by other operating systems. For example, Sonic, which is an open source option. I'm showing here another benefit that it comes with Cumulus and Mellanox together. So a combination of a very strong operating system Linux based together with our hardware, our ASIC inside, which is Spectrum, which differentiate ourselves against many vendors which are using merchant silicon, mainly from Broadcom, is the fact that if we take virtualization and VXLAN as an example, we can do much more tunnels, we can do much more VTAPs. We have no compromises when it comes to features, no loopbacks, all the ports are capable to do VXLAN. We actually have some features that are supported only by us. For example, if you have an environment that is using RDMA over converged Ethernet RoCE and you want to combine it with VXLAN, for example, NVMe over Fabric in the front end, you will find that Mellanox Cumulus is the solution, and so on and so on. So this is regarding Cumulus, still commercial. I want to talk a bit about open source option and ask the question, okay, why open source in the first place? And actually, I want to focus on Sonic because this is de facto the strongest open source solution today as a network operating system in the market. So why in the first place to go with such an option? So first place, because it's much more mature. So Sonic today is actually having a very large ecosystem of vendors and contributors around it. It's also invested in something that many companies invest in the entire world. So Microsoft is definitely the biggest one, but also Mellanox, also Arista, also Dell, also other companies, many companies, Dell, as I mentioned, and other companies are also investing a lot around Sonic. The feature set is getting much, much, much bigger. And there is a lot of support option today, which is more completed when it comes to Sonic, and a lot of deployments around there with Sonic. I want to show you this slide, which is coming from an Azure blog, which is interesting because it's something which is very unique to Mellanox. You see here that the only logo that appears on the 3 layers is actually Mellanox. And the reason is because we are an ASIC vendor. So we are on the merchant silicon part. We are doing systems. And we are doing application. And this is something which is very, very unique, I think, for us. And this is why we actually can provide an advantage when it comes to support.
Avi, we cannot hear you anymore. I think you muted yourself.
Okay, can you hear me now?
Yes, we can.
Okay,
Thanks.
Thank you. So another big question, who should go Sonic? Who should go Sonic is a very important question. Actually, we're asking it. Yeah, I'm sorry, some about the background noise, but you know, it's about working from home. I'm sorry. So who should go Sonic is very important because it means basically, and we're asking ourselves all the time, the question also when we're actually interacting with customers. So Sonic is not good, or open source is not good for any customer, and the reason is because it actually requires a certain scale. If it's a small scale, Sonic comes with some complexity. So sometimes this is not the right choice. So we need to be very honest with ourselves and with the partners that we're working with. So the guy that should go with Sonic should be serious about open source, serious about automation, serious about scale, as I said. The use case of Sonic today, as they are born from the Microsoft use case, is actually something which is typically today more layer 3 to the host. There are more and more contributions inside Sonic, so very soon we're going to see also VXLAN, we're going to see other features. There is already a nice portfolio inside Sonic, but still the use case is typically layer 3. We should be very honest about that. And maybe even more important, who should not go Sonic? Well, if you're looking for a turnkey customer or a turnkey solution, small deployments, not very technology oriented, then Sonic is probably not the right solution. And I think I have maybe 5 minutes, and I think I cannot finish the session. We're not talking about telemetry, because telemetry is something which is important always in any, I think, modern data center discussion. I'm going to present one feature, is a cutting edge feature from Mellanox, which is called What Just Happened. It's part of what is called stream telemetry or real-time telemetry. Now, it doesn't mean that we don't support the traditional telemetry, which is counter-based telemetry like SNMP and flow telemetry, SFlow and so on, logs, obviously. So it's just one piece. But just to show you about, because the networks are becoming more complex, how it's important to have such option. So what just happened basically is a feature that starts from the ASIC. Our ASIC has the capability to understand that there is something wrong happening on the data plane. So we are talking about data plane anomaly. That means that you have a packet that was supposed to come in port 1, goes out in port 17, but for some reason it was dropped. Why? Because of layer 1 issue, flaky cable, or maybe layer 2 MAC mismatch, or maybe an overlay encapsulation error, or maybe the buffer was full, or maybe a wrong ACL was configured. So as I said, it starts from the ASIC. Our ASIC has a capability to understand that this something went wrong, and it actually pushing up the packet to the software layer, the 12th tuple, the header, not the payload, and basically serve it to the end customer and saying, look, this packet was dropped, and it was dropped in this timestamp from this source MAC, destination MAC, source IP, destination IP, for this exact reason. What is the benefit of such feature, which is a real-time telemetry? Look at the alternative. If you're looking, let's say, if you don't have this capability, then basically what you will get in the same scenario of, let's say, a dropping packet, it's just one counter going up, args discard in IFMIB, or maybe some mentioning in the log. So actually, the benefit is huge. And what I wanted to say here, without going into details regarding what just happened, is that it actually supported not only in Onyx, but also in Sonic, which is an open source option, and obviously Cumulus. There are no compromises when talking about telemetry and advanced telemetry features, also when actually using open source options.
Avi, just let me tell you that we are towards the end of the half hour. Actually, I think it just finished. So there might be people moving to another webinar starting now. How long do you need? Because we have like 5 more minutes, and then we really have to drop the session to prepare the next one.
So I just finished.
Okay.
So actually, here you see, kind of the Grafana way to look at what just happened. But at the end, I wanted to say that to close kind of the loop, we're offering different, obviously, operating systems. We can have maybe a combination sometimes, because maybe Sonic doesn't fit the leaf when it comes to VXLAN. Maybe we can put it on the aggregation level and do the part of the VXLAN that he can do right there. Maybe later on also, when you have the features also on the leaf, maybe do Cumulus on the leaf and Sonic on the spine. So the flexibility is really great when you're using open source, open networking option. Everything is using at the end actually the same protocol stack, FRR. And this can be done in different hardware systems. It can start from 10 to 400 gigabit in an end-to-end behavior. And this is, I think, everything from my side. So I don't know if we have time for question, Luca. You can tell me.
We actually do have time. I have given Riccardo the option to unmute himself. Actually, he's unmuted, so I think he would like to read you a couple of questions that have come through.
Mm-hmm.
Absolutely. Thank you very much, Luca. Thanks everybody for participating to this session. And thanks, Avi, for the passionate presentation of PAM4 and 200 and 400 gigabit, how quick the technology moves. We have first question from Blake Willis, who asks, what do you think a data center terabit Ethernet will look like? More PAM levels above PAM4?
So yes, the industry is looking at 800 gigabit and more, but I think, we are kind of, that will happen, much later than now. I think that today, well, it depends on the use case. The typical data centers are still sitting on 25, 100 gigabit. As I said, hyperscalers, maybe AI and more advanced workloads will move to 200 and 400 gigabit. And then later on, we'll see even more than that. There is no other way because we need more throughput.
Understood. And second question from Gabriele Lospoto, thanks for asking it. With respect to WJH, what just happened, how much is it just? Is it based on messaging?
Okay, so the just part means that it's actually giving you real time what just happened just now. This is the terminology, just to make sure we are all clear about that. And the idea is, so basically, it starts from the ASIC, as I said. The ASIC is self-aware about what happened and is pushing it up to the software and saying, look, this is what just happened right now. We are keeping, obviously, a database inside the switch. It's a cyclic database. We're not going to interfere with the data plane. And eventually, you can actually use some complex mechanisms to actually show and present, the different events that were happening.
Excellent. And then we have their question from Omelenders. I think it's kind of acronym. Is Cumulus Linux part of Mellanox strategy?
100%. So before I go to the technology explanation, I would say that first, the best proof is that NVIDIA networking 1 minute after the closure of Mellanox actually signed the check or the agreement also with Cumulus. So this is, I think, on the business side, obviously the evidence for that. But beside of that, Cumulus is our #1 operating system by far. We're going to focus on that. We're going to focus on Onyx also and Sonic. In sometimes, I think with some use cases, we go with Sonic because we think it's a better option. We recommend to do that, obviously. We think there are many benefits of using open source, as I explained in certain scales. Sometimes a combination, we have a very unique option to provide Cumulus and Sonic together and provide full support for that. That's actually going to reduce cost dramatically. And Onyx will stay there as a traditional operating system. There are use cases, for example, storage. We have a package worker solution, which is using Onyx. So definitely Onyx is going to have some segments, but Cumulus is going to be by far, I think, for the core of the data center, our #1 option.
Thank you very much, Avi. And I would like to add, as we're in question and answer time, I would like to add a little bit of perspective to this last question by reminding the reasons why NVIDIA, Mellanox, and Cumulus came together. And it all starts with a vision, the vision that the server is no more the computer. The computing unit is no more the server. The data center is the computer. So we need to think at a bigger scale. We need to think about the data center. And the data center has three aspects. It must be accelerated. And if you talk about acceleration, think about the GPUs, you're talking about NVIDIA. The data center must be disaggregated. And this is all about the speech that Avi gave us, disaggregation, the difference between hardware and software, and the possibility of mounting the right software on the right hardware for the right use case. And the third aspect of the data center is actually, it must be software defined. And here Cumulus come into play. Software defined also mean plug and play, plug with a module, software module that can add and provide additional services. So all of the data center comes around these three aspects. They are all now covered with this merge of NVIDIA, Mellanox, and now Cumulus. And with that, I would really like to thank you very much for your participation.
Thank you very much. I think that, seeing people running over the half-hour allotted time means that there's been interest and engagement from the audience, which is good. So let me take this last little moment just to thank Mellanox/NVIDIA for being a platinum sponsor of our event. And thank you everyone for attending the webinar, and Avi and Riccardo for hosting it. Thanks very much.
Thank you, Luca. Thank you, Alessandra. Thank you all. Bye-bye.
Bye-bye.